Right, so we're going to talk about arithmetic in Z adjoint X. And so what we mean when we say arithmetic is we mean, what are the rules of addition and multiplication? Okay. So let me remind you of some of the rules, some of the ways in which we add and multiply polynomials to give you an idea for why writing down these definitions is a little bit more involved. So suppose, for example, we wanted to go over adding. Well, we have some polynomials, maybe something like this as one of our polynomials. That's some p. And then maybe we have a q, which looks like, I don't know, 2x plus 4x squared plus, um, you know, negative 2x to the fifth. Or maybe negative 3x to the fifth. I don't know. So, okay, so how do you add these? Well, you know that p plus q is you combine like terms, right? So here, really what in order to properly combine like terms, we kind of have to rewrite P and Q. We have to view P as 1 plus x plus 0x squared plus 0x cubed plus 0x to the fourth plus 3x to the fifth plus 0x to the sixth plus 1x to the seventh. And then we have to view Q, the thing we're going to add to our P, as 0 plus 2x's plus 4x squareds plus no x cubes plus no x to the fourths plus negative 3x to the fifths plus no x to the sixths plus no x to the seventh. So a couple things here. When we don't write a coefficient, we'll assume it's 0. Okay, that's fine to do. We're going to have in the notation that we have for polynomials. It could be that some of the coefficients are 0. That's not really the problem. The problem is that P and Q could have different degrees. So if we look here, the degree of P is 7 and the degree of Q is 5. So how do we fix that to add them? We kind of have to artificially extend the degree of Q, of the smaller degree term. Now there's a couple of ways to go about doing what I'm about to do. That is writing down a sensible addition when your polynomials are generic. They're not explicit like this. I'm going to pick one of the ways, and it's going to be to artificially extend by zeros, but there's other ways that you can go about it that are in other introduction to abstract algebra books. Now, since we wrote this down, let's complete the sum just so we see. So we get 1 plus 0 plus, the coefficient here is a 1. Sorry, I didn't write that. 1 plus 2x's plus 0 plus 4x squareds plus 0 plus 0 x cubes plus 0 plus 0 x to the fourths plus 3 plus negative 3 x to the fifths plus 0 plus 0 x to the sixths plus 1 plus 0 x to the seventh. So that's how we would combine like terms, and then what we would get is 1 plus 3x plus 4x squared plus no x cubes plus no x to the fourths plus 3 plus negative 3 is 0, no x to the fifths plus 0x to the sixth plus 1x to the seventh, and we usually write that in shorthand as 1 plus 3x plus 4x squared plus x to the seventh. All the 0 terms we don't write. But in order to properly define this, when we don't necessarily know what the coefficients are, we have to do something that makes the terms match. So what's the rule? So given two polynomials, p and q here, we want to say what it means to add them. What we can do is we can write out what p is. So it's a bunch of sums of monomials, and we can write out what q is. I'll use b's for q. But the degree of b might be different than the degree of q. So n and m should not necessarily be the same thing. And then what do? Well, we have to say if n is bigger than or equal to m, extend q by 0, or let me write that slightly different. If n is bigger than or equal to m, we're going to set bk to be 0 for k is 1 more all the way up to n. Now it could be that n is equal to m, in which case we don't do this, and they're the same degree. But if it's bigger, what we're going to do is we're going to extend by 0. Okay, then we can think about q as being b0 plus b1x all the way up to bmx to the m. And then we're going to get further terms now. And these further terms that we're adding on are 0. This whole expression here is a 0. To mimic, again, what happened in this example. To really properly add, we had to artificially extend by 0. And so that's what we're doing. We're going to artificially extend by 0. All right. Then, once we have that, p plus q is combined like terms. So a0 plus b0 is going to be the constant term. a1 plus b1 is going to be the linear term, and so on. And you're going to keep going until you get an plus bn, and this makes sense to write. Even if bn is 0, it still makes sense to write. So that's if n is bigger than or equal to m, we have to extend q by 0. If n is less than or equal to m, the other way, we're going to extend p by 0. So we'll set ak to be 0 for k is n plus 1 all the way up to m. That situation arises when the degree of q, so there's more m's than there are n's, or m is bigger than or equal to n. Okay, in which case if we sort of artificially extend q by 0, then we get, then p of x we can rewrite as a0 plus a1x plus plus plus. There's going to be still this anx to the n, but now if m is bigger than n, we're going to artificially extend by 0 till we get to amx to the n. Again, this is just 0, so it's not changing p at all. So then we have this, and we defined p of x plus q of x as the similar thing. We combine like terms. So a0 plus b0, a1 plus b1, all the way up to, in this case, am plus bm, because m was the bigger of the two in this case. All right, so this is how we define our addition. Notice the addition is quite complicated, and really there are nicer ways about this. I think this is the easiest to understand way, where you just have to extend one of them by 0 so it makes sense to combine like terms. And that's all that's really going on. But when you're trying to prove properties of this, like suppose, for example, you wanted to prove that addition is commutative. It is in fact commutative. You can see that addition is really just, you're really just adding integers here, and we know addition of integers is commutative. But suppose you wanted to prove that. Well, you'd have to be able to add them first. And so you would say, well, if n is bigger than or equal to m, we extend q by 0, and then we look at p plus q. Otherwise, we extend p by 0, and then we look at this version of p plus q, and then you prove something there. And so anyways, this is the definition of addition for this set of polynomials with coefficients in z. And in the next video, we'll tackle multiplication.